Okay.
So yes, thank you very much. I'm very grateful and happy for being given the opportunity to speak, and yeah, and I also use this occasion to thank for a wonderful convention in Buenos Aires when we met there. I had really was really fun, but both scientifically and non-scientifically, and yeah, I hope I'll be back in South America soon. As people are so nice and the food was amazing, and yes, everything was good. So I hope I'll be back sometime really soon. Yes, and of course, thank you all for coming. Today, I would like to talk about some work in progress on Hochschild cohomology of monads. So I don't know. I hope I spell this correct. I should not try to read it, but so yes. So I recall Hochschild's original statement of how he initiated Hochschild cohomology, and this is the combinatorics. There is, I mean, this is perhaps well known for everyone, but it gives some sense of the basis for how we should make a monad to fit into this framework. So Hochschild cohomology were introduced by Gerhard Hochschild in 2 papers, 1945, 1946. And the idea is that we can get homological information about a ring or about an algebra by study tuples. So K tuples, so with K occurrences or the ring cancelled with itself. Or what we really study is map, but not the map. It's what is happening if we do the procedure, which I will explain on, which is probably known for everyone here. I don't know, but let me explain it, because this combinatorial things we will come back to later. So the point is here. You look at what is happening if you increase the size of the tuple with 1, and you use F to get an other map with a larger or larger tuple into. So it could be R itself, or you can have values in an arbitrary bimodule. So the way, so not advisement here now, but the way this is done, I mean, it's basically 2 parts here. I mean, one part is the inner parts, so it's one sort of also this can be grouped into two main parts. So the inner part is you apply multiplication to each adjacent pair of rings, and then you will get R K tuple, and then you can apply F to this, and you get this. So this will actually define what we wanted, a map from a K plus 1 tuple into X. So apply multiplication, we get a tuple of 1 size less, and then we can apply the map F again. And there are also 2. So let me take this away. There are also 2 outer. So I mean this one group of summands, and there are 1 outer group, which you apply F now to the tuple with K first occurrences, so we can apply F here, and then you get something in R. Oops, not correct. get something in X, tensor R, and now we can apply the bimodal structure to get them up further into X. And you can do the similar, of course, with the last occurrences. And if you take the alternating sum of all these things, this defines a differential. So it turns out that it defines a differential, which is mean this original statement by Hochschild, Hochschild cohomology. So, but of course, I mean, it's not so much that go into these things. So we need a ring, a sort of algebraic object, with some sort of tensor product. And what I did not talk about is that you need some unitary condition, and it, in some sense, this tuple have to be managed in some way. So you need some associativity. So did this work for a very general setting, for a unitary ring, which is associative, basically. But you can, of course, apply more structure to it. So I mean, now this page here is almost blank. So you can do it with a K algebra with a tensor product with K, and then now K play the role as unit. So I mean, this has been, some examples there have been important for various questions in homological algebra. I think perhaps one, I'm not like full overview. I'm not an expert here, but Happel, 1989, had this question: if you can have finite global dimension, then the Hochschild cohomology ring would also be a finite dimensional, something like that. But Buchweiz, or Green, Matson, Buchweiz in 2005, they found a negative answer for this with quantum complete sections. So I mean, this has been an important thing or invariant to study algebra. So more complicated algebraic objects with more structure. And of course, in ICRA, I enjoy Christel's talk on monomial quadratic form. So simple extension, which is an other technique. So this to actually compute Hochschild cohomology, which of course many of you know, it requires advanced homological algebra. So this will not be I mean, this will not be main topic for this talk today, but I think it's important to have in mind that it's actually deeper structure we are interested in Hochschild cohomology. Often, not that this can be understood on the level of ring, but in some sense the inbuilt structure that you have in for example in algebra. So other stuff. So the question is, or what I think about, I mean, is, do you need some formal some additional data for this thing, or is that something you can sort of build into the definition? I mean, this is kind of two perspectives. In some sense, I mean, to motivate a bit for what is coming later, but I don't know if so we are warned that monads will play a role in computing. I think not, but this is in some sense motivation for monads, or for play a role in monad. You have a map from an object to itself, so it's in a category. So here there is some structure here that some sense take care of the structure of the basin. So I mean, this is something that is inbuilt to the map and will not require additional data. So I meant this to be some motivation for why this thing should be interesting to study and perhaps define Hochschild cohomology for. Okay. So as I mentioned, for I mean, if so not all this advanced homological algebra that you really need to compute this thing. I mean, this is a very hard problem for a ring to compute its Hochschild cohomology. But if you think about Hochschild's original definition, it was not so much that went into this thing. So how was it? It was you needed a ring or some kind of algebraic object with a tensor product, and yeah, some unitary things which we didn't actually see from what I saw. So this I think this applies for a monoidal category. So that really means you have a category with a tensor product and unit, and you have some associated uniter, left uniter, right uniter, which you can assign the tensor unit with the object, and you can move parentheses basically. And in there you can define a monoid, which consists of an object. So an object M, a multiplication rule mu from n tensor m into m, and a multiplicative unit from 1 to n. You can, of course, do a lot of things with monoids and with monoidal categories. So one way you can study this is to, in some sense, manipulate the tensor product, or to have to use, for example, a co-end as tensor product, and this is something it gives understanding of Hochschild cohomology in a homotopical setting, which has been studied by Catherine Hess and Alexander Berglund in some papers. So you get some. I mean, I think they were interested in co-algebras actually, but they defined Hochschild cohomology for this gadget, and I think they got to understand the homotopy theory of this gadget. So I mean, my point is really there is the potential here. You can apply some additional data to this thing, but I mean, this is I believe I have the impression that this will be a lot of things to take care of in the end. All the additional data that comes with the monoidal category itself, or the way you place them monoids, or something like that, if we want to do something interesting. So we have backward in front of our head all this advanced homological algebra that is needed. Homology, then you have a complete algebra. So I mean, I think this also is some kind of motivation for again, if you look at a monoid, we'll come to that soon. It consists of a map from an object to itself. So again, it belongs to a category. So I think there's a potential there. I mean, this is really informal. This is some thoughts. I hope that's allowed and work in progress. So that's really my motivation of why to study Hochschild cohomology of these gadgets originally. Okay. So monads really live. So they live in what is called a bicategory. Bicategory consists of objects, so which I will denote by small Latin letters. Consists of one arrows between the objects, so as usual in a category, which I will denote by lowercase Latin letters again, and it comes with a composition rule, which is referred to as horizontal composition. So composition of one arrows. And for each object, you require an identity. So it's basically the same thing as for an original category, but there is a difference. Well, I can back to that really soon. And you also have a notion of two arrows between one arrows. So I will denote them by try to do double arrows and lowercase Greek letters. And you also have some notion of vertical composition, which is a composition of two arrows. And for each one arrow, you have an identity map, which I will denote by iota. So there are several things that go into this. I'll only mention a few maps. So I'll mention the associator, which it's a two arrow, which is invertible. That to each tuple of this form, assign it to tuple of this form. So you can basically move parentheses. So the horizontal composition is not associative on the nose, but up to this relation. So, and yeah, this is I think I forgot to mention, but this is invertible, but invertible on the nose. I mean, in terms of another two arrow that is actually equal to the identity two arrow. So,
Magnus, excuse me.
Yeah.
Is that the meaning of weak, or is it something else?
The meaning
of weak.
Yeah, it's meaning of weak. So,
Thank.
I think I have recently got a bit more control about the usual terminology in these things. I think so. I better be safe than sorry here and call this a weak bicategory. But I think bicategory is usual reserved for this thing that Benabou defined, which is this is really a weak two category. So MacLean talked about two categories for to describe the categories of all categories with so categories, factors, and natural transformations, which is strict all compositions associated, yeah, of course, on the nose and identity on the nose. And there is also a third thing here. It's this Charles Eresman this double category, which is an other thing again. I think this is something internal category of all categories or something like that. But I'm not so familiar with that. But it's yeah. So yeah, good question. Yeah, very good question. So yeah, that's yeah, really what refers to weak.
Thank you.
So so just so I mean it's I've perhaps been a bit silly here because I had the parentheses on the left here. So this means that with this convention here, when you have a chain or morphisms, you actually start on the right at the end and then build up. So this is actually what this means. And here you in some sense do the opposite, and that's perhaps the more natural thing to and then compose further. But yeah, let's stick to this convention that is start on the right here. And you also have this unitor. So if you compose horizontally with identity, it's not equal to F on the nose, but you can assign it to F via this invertible two morphism. And similar if you compose with the unit on the left. Okay, and there are some more maps, especially how you can connect the horizontal composition with the vertical composition. So I mean, so this is so this is the domain, or this 2 arrow, and this is the codomain. But if you compose here, you also want to relate this with the composition. I mean, the vertical composition of this two. So there's certainly some relations and diagrams there, which will be important to make the definition of Hochschild cohomology to make sense. But I mean, we will be sitting here tomorrow, I think, if we will go through all this list of axioms and requirements. But remember that we need some procedure to assign horizontal composition with vertical composition and vice versa. So this actually can play together in our structure and not some independent stuff. So there are some conditions and diagrams there that we are skipping. I mean, it's much later here and then in South America, so tomorrow is closer to me than to you. But let's skip that for now. I'm prepared, and it's perhaps thing that is a bit annoying, that we will require this. So this is a category, the category of one homomorphisms between A and B. So it's a category in its own right, because also what are the objects? There are morphisms between A and B. And what are the maps? There are two morphisms between these morphisms. So this is a category in its own right, and we require this to be an A/B. We require all these to be A/B categories, which means that they are enriched in a building group. So you can basically do algebra on the maps, or plus or minus this stuff on the maps. So now we are in position to define monads. So a monad consists of the following data. I mean, so yeah, it consists of the following data. So it's an object together with a map, a one arrow from A to itself, and two arrows. So there is a multiplication rule. So if you compose T with itself, which is perfectly fine thing to do, then you have a multiplication map or multiplication rule that assign this back to T again. And you have a unit or multiplicative unit, which I denoted eta here, which take the unit of A, or the identity map. Sorry, identity map, and assign it to T itself. And this should act as a unit for the multiplication rule. So you have something here. So I mean, you have something here. You can compose T with itself, so we can make tuples, and you have a unit which was some important for Hochschild cohomology. So I mean, I think so we are in a good situation for try to define Hochschild cohomology. But with this map that can exist in some categories, so it has some structure that it should respect with the category it lives in. So this should okay. So such that the multiplication is unitorial. So it means it doesn't the unit doesn't be affected by the multiplication by this map. Or I think we can perhaps we should try to draw this a bit differently. So I choose this color visible. So if we start with T here, we can. So it's visible. So we can here add the identity map of A on the right. So we apply rho T inverse, and here lambda T inverse. And then, so this is, I mean, the opposite of assigning a unit to a map, that you create a unit, so this should be invertible. And here we have the same thing on both sides. So if you start with T, and you do this procedure by getting an identity on the right and the left, and then you take this unit map, this unit 2 map, and then we of course will get this gadget and apply the multiplication there. So this really means that this is a unit for the multiplication. So eta is a unit for the multiplication by means of this diagram. And the multiplication is associative, so in some sense it respects alpha. So so if you apply the multiplication map on the left, and then apply the multiplication map again on this thing, this is the same by applying alpha and apply multiplication map on the right, which actually means on the left, since opposition. There's the chain around and then apply it again. So this diagram commute, it means that the multiplication rule is associative. So this is how this so this unit and multiplication play together with the algebraic structure to actually get what we really expected from rings or algebras. I mean, and we are just now, I mean, scraping the surface for this thing. So there's, I mean, for now, no additional structure which we were motivated for in case of this questions and homological questions and conjectures. So we can define a left module of T. So it's a left module of T. So we apply a map on the left side of A. So a left module consists of a map of one arrow on the left side of A, together with a 2 arrow that assigns the composition of X and T to X itself. So quite similar as for left modules in the usual setting, right? And in the literature, this is often called T algebras. I think T, it comes from triple, which is, I mean, the original study of monads was from adjoint pairs. So I think that is where the name comes from. And I mean, the modules, they have a lot of how do you say it? They have a lot of street creds, so they respect the unit of the monad in the sense that this diagram commutes. So if we get the identity map on the left and the unit, so you get T, and then apply the module action, we get to what we started with. And it's also associative. So here we are missing alpha, so it should be T, X. So if we apply the multiplication map and the module action, and for the module action, you get the same thing basically. So this is what we are used to for modules. So I mean, this is very good. And same for right modules. So here we now have a one arrow on the right side together with an action to this composition. So in some sense this module action, it yeah, it's associated T. So Y composed with T with Y itself. So you know how the you know how T on this side, right? So we apply this. So we have a map on the other side together with this action. So similarly, it respects the unit, and on the right side, and it's associative. So in Hochschild's original definition or interpretation of Hochschild cohomology, we wanted some bi modules right? We have values in bimodules, so we perhaps should define bimodules for monads as well. So here I call this TS bimodule, which consists of the following data. So C, sigma, and omega. So C and sigma, C and sigma is the left T module, and C omega, so C omega is a right S module with a different monad. So how does this really look like? So we have C here, and we have S on the left. We have S. Yeah. So we have T, and we have the module on the left, and we have now S, then the module on the right. So we should be applied our map to the left or the right, and this is the same map with these two actions. So nothing new here. This is exactly what we discussed for left and right modules. And this should so the sigma and omega here, they should act together. So I mean, if you apply sigma, then omega is the same as applying the associator and omega and then sigma. So we get the same thing in the sense that this is okay, right. So now we have monads. We did a bit field trip on how these things work for modules, left and right modules, and now we define bimodules. So now this is all we need basically to define Hochschild cohomology. And but in Hochschild cohomology, the bimodule was an RR bimodule. And I'll be a bit boring today and do the same thing to use a TT bimodule. Here with this S, it can just be different, of course. So, so we let T be a monad and C sigma omega be a TT bimodule. And now we will study tuples of T. I mean, for rings, this was not easy, but they are associative. So the tensor product is associative on the nodes. So we can basically remove the parentheses, but it was not quite that easy with monads, at least in the setting that we looked at. So we have this tuple here, where you have a pair in the depth, and you compose with T successively to get K occurrences in there. So I mean, again, the arrangement of parentheses here really means that you start on the right of a chain like that. So you start on the right. So we have T. So that one, and you compose it with T. That one, and you go on like that until you have K occurrences of this T. So I mean, it's not crucial, but we need some kind of procedure to know these parentheses, since they are not associative on the nodes anymore. But we can use the associator to arrange the parentheses how we want, which I will say a few words about. And we now look at. We should now look at maps into set. This is how I started the talk. So now we are basically back in this setting that Hochschild used to define Hochschild cohomology. So we look at chain. or two, or two, I mean, with, so the gadgets here are two homomorphisms, and the one is of one homomorphism that should make this map work for larger tuples. So there is, I mean, two parts here and need to be done differently because we have this unit map in the beginning. So the first differential, so we will take now phi from the identity to z, should now be mapped to a map from t to z. So by the differential applied to this map. And that goes by following. So now we start in t, so we should have a map from t. We can add the identity on the left or on the right. And then we apply phi in the right place. And then, so now we get a one morphism. So C composed to T, T composed to C. That's what phi is doing. And now we use the right or the left module action or bimodule action to get to C. So this sum or difference here, that is the first differential. So there is a very strange thing here, which was mentioned but not done in detail. This is, if you have here, this is a composition of one arrows. And here, this is a composition of two arrows. So how is this is really possible? This is the thing I skipped. So this is how vertical and horizontal requirements that they should satisfy to get this work. I mean for if you use tensor product here, or have some, so for as with the Hochschild's original definition with rings and tensor product, algebras and tensor product, this is no problem because of functionality of the tensor product. So you can always tensor two maps. But I mean, here is this is some strange thing that but it works because of this horizontal and vertical composition, how they act together. Okay, so that was the first differential. Or I'm wrong. I'm absolutely wrong. This should be the zeroth differential. Should be the zeroth differential. Sorry about that. Should be the zeroth differential. And for the higher differentials, again we had this intuition from Hochschild's original definition. So it should be two main parts there, or two main groups. We have the inner ones that we apply the multiplication map to adjacent pairs. This is what is happening in this pair. So again, you should have a map from TK plus 1, this tuple, into Z, or into C, sorry. So here we need to go into the depth of the tuple. So let me scroll it out here. So it is possible to apply the multiplication map if you have. So we should have we should isolate an adjacent T set. So we will isolate a pair of these occurrences of T, and that is actually not so hard. We don't care if it's, I mean, on the surface or in the depth, because we can apply maps in the depth. I mean, this is again a property of this horizontal and vertical composition thing. So here, I mean, if you want this pair to apply multiplication map in this pair, we can just use the associator on the triple inside there. And similarly, you can ignore the first part and then use the associator to get an isolated pair. So this is what I tried to formulate with this map. I mean, it's correct, but it's a lot of indices here. I think, but I mean, the idea is to isolate pairs. So we isolate a pair, we should apply multiplication map to, and then now we get the k tuple, and then apply phi, and we get values in the boundary. The outer parts, they are one outer part is easy because with the configuration of parentheses we use, this is so we have actually isolated k pair here at first. So I mean the tuples is, I mean, we composed on the right, which actually means that we started in the end, right? So we actually have this free by definition, and then we can apply phi directly. But on the other one, we have to do some work to move the parentheses in the correct place, so we get t on the left side instead. So it's a bit work, but with the associator, so you basically move one parenthesis on the at the time. So at least I have managed to do this in some very efficient way. But I mean it's efficient enough. It's just composed associated with itself many times, and yeah, and then apply p again and get this gadget and apply the left modeling action, and you get C. And this is cochain complex. So the differential, when you compose them, you get 0. So we can define cohomology in the usual way, now with values in C. So I mean, I hope it survives all this combinatorial. So I'll just mention that. So I think, as all you know, that the zero cohomology group is the same as, I mean, it coincides with the center, right? Center of a ring or center of a bimodule in the classical sense. So I use this. I don't know if this is I perhaps been I'm not get any complaints about this, but I call this quasi center for a monad. that this zero cohomology thing is a quasi center for, I mean, for the bimodule actually here. But if you replace it with T, you get a quasi center for the monad. I mean, with this, so this means, so the cohomology means that this thing here, I mean, this thing here is 0, which means that, so how can this be 0? Yes, you have to do actually the same. If you start at T, go here and go here, so we actually get this diagram here. So the center is all these that are that make this diagram. I mean, and that is exactly how the first cohomology is defined. And of course, there is also some, if you read Happel's paper, he has a lot of interpretation of the low-dimensional cohomology groups. So, but I didn't want to speak so much about that. I want to say a few words of the cohomology ring, if time permits. It's okay. So, so we define a cohomology ring. As usual, the sum of all the cohomology groups, and the cup product on this cohomology ring, it should be an operation. So, I mean, these are really groups, so it should be an operation from. So it should be second superlative. Yeah, sorry about that. And so on an operation of degree 0, right? So it's it takes two. I mean, this, you do this for representatives for this residue classes in cohomology, right? And if this is of degree m, Mikey, and G is of degree n, November. The coproduct of these two is an element of degree m plus n. So how is this defined? So there is, there is 4 things we need to define. And I think this is also in the classical setting because you have this identity thing in the cell cohomology. So we want something that came from the tuple T m plus n into T itself. Oh, I forgot to tell that thing. So now we replaced Z by T. That's cohomology. Or otherwise we need some relative things, something like that. So now here, set equals to. Okay, I think we can. Let's just look at the last one. So we start with a tuple like this, and we apply phi. And so we get this tuple, and now we arrange all the parentheses. So we get T isolated, and then we are in position to apply C on the other side. And now we can apply the multiplication on this, and we get T. So this is how it is defined, and actually after a lot of work, so I was cheating. This is graded-commutative, which means that if we interchange the order of phi and C, this only varies with -1. So if you interchange phi with C, this will only varies with this design as usual. But there's some shuffle work here, and then this is the way I did it was just following Gerstenhaber's original argument. So I don't mean to be self-promoting, but this was something I also did in paper with monoids for my thesis some years ago. If I can just have 1 second at the end, so we should always have an example, right? so actually a natural example came from adjoint pairs, and I think this is the original adjoint pairs or adjoint pairs of functors. So which is I think this is how monads were studied originally. So adjoint pair, it defines a monad. So adjoint pair, left adjoint, right adjoint, with units eta and co-unit epsilon. Define monad. So the object is the category C. The one arrow, we define T, which is L composed with R. And the unit is defined by the unit. So it's the same thing for the adjunction and the monad. And the multiplication map is defined by the co-unit, but with identities on both sides. So this provides a map from T times with itself into T itself. So, okay, I think I'll stop there. Thank you very much for the attention.
Thank you. It's great.